So we've said that as a car changes direction, there's an acceleration on the car. Now this is why it's really important to secure all the objects inside your car. If your car changes direction and experiences an acceleration, it doesn't transfer that acceleration to unsecured objects. So if you leave something sitting on the back seat and then turn a corner, the only force between the back seat and that object is the frictional force. And if the force, due to the acceleration of changing direction, is larger than that frictional force, then that object is going to start to move. And this can be really dangerous. This is also why people wear seat belts in the car. You need to wear a seat belt so that it holds you in place against the car. Then if the car comes to a stop suddenly, you do not keep on going like Newton's first law says you should, because an object in motion remains in motion. That seat belt provides a reaction force pushing you back against the car so that you and the car remain connected. If you didn't have a seat belt and you were in a crash, it's quite likely that you would fly through the windscreen, and this would do even more damage to your body than the seat belt does. So let's now consider the motion of an object which is following a circular path. Let's imagine that it's got some circular path, and we'll imagine that it starts at position 1 and moves to position 2. Between position 1 and position 2, there's some change in angle which we can represent as delta theta, as shown on the diagram. Now, we've said that speed is just equal to the distance over the time. For circular motion, we've got a very similar concept. It's called the angular speed. The angular speed is equal to the change in angle over the time. It's generally measured in radians per second. So in a circle, there's 360 degrees or 2 pi radians, and we can use that relationship to convert angles from degrees to radians. So if you have an angle in degrees and you want it in radians, you need to divide by 360 and then multiply by 2 pi. What we're going to do now is use some circle geometry to show the relationship between speed and angular speed. So we'll be showing the relationship speed is equal to the angular speed times the radius, or v is equal to omega r. So we're using the same circle, and we know that the angular speed is given by the change in angle over the time. So that's just what that formula says. Omega standing for the angular speed, and delta theta is the change in angle. And now what we need to do is we need to use some circle geometry. From circle geometry, we know that the arc length, which is this length here, we can give that the symbol delta S, standing for arc length. And arc length, delta S, is equal to r times delta theta, where r is the radius of this circle. So r times delta theta tells us this length here. And so what we can do is we can rearrange this part to give us that delta theta is equal to the arc length over the radius, and we can now substitute this back into this equation. So let's call this one equation A. So we can put sub into A. And so we've got omega is equal to delta S on RT. And now delta ST, delta S, that's the arc length, which is the distance this body has travelled in this time. So delta S divided by T is just equal to the velocity. So delta S over T is equal to the velocity, just the distance over the time. So we've got that this is equal to V on R. And so this tells us that V is equal to omega R, just rearranging, multiplying both sides of this equation by R.